Yeah, I guess we're gonna continue looking at some Treewidth now. Thank you for the introduction and thank you to the organizers for the opportunity. Let me just okay, you can see the presentation
Yeah,
fine?
yeah, I see it
Okay,
very.
perfect. Um, I don't know why it's doing that. So I'm gonna talk about Treewidth as it relates to outer string graphs, which is a class of graphs of intersection graphs of curves in the plane. And this is joint work with Maria Chudnovsky, Sepper Hajebi, Sophie Spurkle, and Bartosz Walczak. So I guess we just saw a bit of Treewidth, but for those who don't know, it's essentially a graph parameter that in simple terms tells us how complicated a graph is. So I'm not gonna give the exact definition, but it's studied a lot because for graph classes that we know have bounded tree width, we can do a lot of things that we don't know how to do on general graphs. So for example, there's a lot of NP-complete problems that we can solve in polynomial time on graphs of bounded tree width. And there's a lot of structural characterizations of graphs of bounded tree width that we know about. So it's a very useful property to have bounded tree width, and it's a big area of study. Um, a few preliminaries, I'm assuming most people are familiar with most of these. The one that some might not have seen before is induced minors, so I'll quickly define that. So an induced minor is essentially a minor, but you're not allowed to delete edges. So it's a graph that's obtained from the original graph by vertex deletions and edge contractions, but no edge deletions. And the rest of these are fairly standard. So the most well-known result in this kind of area of study is the grid minor theorem of Robertson and Seymour, which gives us a full characterization in terms of subgraphs or equivalently of minors. Um, so essentially it says there's only one reason from a subgraph standpoint of why your graph should have big tree width, and it's because it contains a big wall as a subgraph. And you can also say minor instead of wall, it doesn't make a difference. And so a big area of study in this field is can we make similar statements, but instead of asking for subgraphs or minors, can we ask for induced subgraphs or induced minors? And so this is a very widely studied topic. And so the main result of this talk, or the main topic of this talk, is this conjecture of Chotignon, which says essentially that as long as your underlying graph G doesn't have one of these two obstructions as an induced minor, so WTT is the T by T wall, or the complete bipartite graph as an induced minor. So as long as you don't have one of those two as an induced minor, then the only reason your graph should have big tree width is if it has an induced subgraph that is an outer string graph that also has sufficiently large tree width. So that's the conjecture, and it's false. And we're going to show in this talk the construction that proves that it's false. So this is the theorem essentially is just stating the converse of this conjecture. And in the talk, we're going to focus specifically on proving property 3 here. And this property 2 is also non-trivial and it requires some work to prove, but it's too much for a 15-minute talk. So we're going to focus on 3 here. And so the constructed graph looks like this. And this is just one example. This is G sub 5, but the family is G sub k for k being any integer. And the construction is essentially as follows. So we start with k paths. So in this case, we have 5 paths. The length isn't super important. So you see here it's 64. And oh, sorry, I think I'm back now. Sorry about that. So we have 5 paths. The length isn't important. There is a reason for it, but we're not really going to get into it. What's important is we start with 5 paths. We put a vertex in the middle of the top one, and we give it a neighbor in each path below. And then we kind of start this inductive process. So now we go to path number 2, we go to the left and the right, and we kind of do the same thing. So we put a vertex here and we give it a neighbor in each path below, and we continue on in this fashion. So this is for 5 paths, but you can continue this for as many paths as you want. And now we're going to get into a bit of the tools we use for this proof before actually getting into the main proof. So one of the main kind of techniques we use in this proof is related to weight functions and balance separators. So let's quickly define that. A weight function is just any assignment of scalar values to the vertices of a graph positive scalar values between 0 and 1, such that the sum of the values of W on all the vertices is at most 1. And sometimes you'll see this written as equals 1. For our cases, it doesn't really matter, but we use the more general, just at most 1. And given a weight function W on G, a balance separator for W on G is a set of vertices that we can cut out from G such that the components of the new graph with the deleted vertices all have weight at most a half. So essentially, we want some set of vertices that if we get rid of, there's no longer any component that's too heavy. And as it turns out, balance separators are very closely related to tree width in the sense that if a graph has small tree width, that means that for any weight function on that graph, we can always find a small balance separator. And conversely, if for every weight function on the graph, we can find a small balance separator, then the graph's tree width isn't too large. And I just want to say quickly, when I say small, what I mainly mean is not dependent on K. So it doesn't have to be like 3, it could be a million, a trillion, but just not like K squared or something like that. Because our proof works for arbitrary K. So as long as we have something that's bounded, not dependent on K, that's sufficient for our purposes. So the next tool we use are called long thetas, which to make it simple, it's a long theta is this graph or any subdivision of this graph. And what is important for this talk is that this graph is not an outer string graph and any long theta is not an outer string graph. So you don't need to know exactly what an outer string graph is for this specifically, because the way we're going to prove that our graphs are not outer string graphs is just by showing that they contain these long thetas as induced subgraphs. So with that, we can quickly overview the proof before we show some of the details. So just to recall, we want to show that if we take an induced subgraph H of G, either it has small tree width, or if its tree width is too large, then it has to be an outer string graph. So recall that G has unbounded tree width because its tree width is dependent on K, which can be arbitrarily large. So we want to show that an induced subgraph H of GK for any K has either tree width under some constant that's not dependent on K, or it contains a long theta. So the first thing we're going to do, we're going to fix H and a weight function W. Since we don't exactly know how to analyze H, we're going to find an induced minor of H called H prime, which we'll define in a second. And using properties of H prime, we're going to show that it has bounded tree width. And so this will tell us that we can find balance separators on H prime for any weight function, but in particular, this W prime, which will be related to W. And using this balance separator that we get for H prime, we can get a balance separator for H. And as it turns out, this isn't exactly enough. We're going to have to take an extra step, which is where we're going to use the fact that our graph is an outer string graph, but we'll see that in a second once we get into the details. So just as a visual, this is something that H could look like. Of course, there are a lot of different things it can look like, but essentially we just choose some of the vertices of G and we say, okay, we keep all of the edges between them. And recall that these aren't exactly edges, they could be paths, but just to avoid too much clutter, we just draw them as edges. They're not so important. And so this is how we're going to obtain H prime. So all of these vertical curved edges, we're gonna contract them all. So these sort of gray clouds that we have over sets of vertices are now one vertex in H prime. So for example, all five of these vertices here in H are just one vertex in H prime. And the way we're going to define W prime is we kind of obtain it naturally from W. So we say that the weight of this large vertex in H prime is equal to the sum of the individual weights of these vertices in H. And one more thing, just terminology wise, we're gonna refer to these top vertices of each of these kind of super vertices as the representative of that respective super vertex. So, for example, this vertex in H is the representative of this whole super vertex of H prime. And so, as it turns out, H prime is fairly simple to analyze, and it is fairly easy to show that it has small tree width. And the way we do this, I'm not going to show the exact proof, but essentially, since this entire block here is now just one vertex in H prime, we can split this down the middle, and then we get two similar graphs. So we get one, which is kind of this left half of the graph, and one which is the right half of the graph. And both halves kind of exhibit similar structure to the bigger graph as a whole. So using an induction argument, we can show that we can construct this graph just using series parallel operations. And the series parallel graphs are exactly the graphs of tree width at most two. So this tells us that we can find a small W prime balance separator for H prime. In particular, it has size at most three, but what matters is just that it's a constant. And so we have a balance separator for H prime now, and we want to translate it back into a balance separator for H. And so the question is, can we do that? And so here's a visual. We have H prime, and we know that it has a balance separator of size at most three. So what that might look like is these three vertices in red here. Vertices, they're super vertices, so vertices of H prime. But you might begin to see what the problem is, which is that we can remove all of these individual vertices from H, and this will give us a balance separator for H. But even though this balance separator X prime has size at most three, we have basically no way to bound the size of this separator for H that we get. Because, for example, this guy has size 5, the super vertex, but recall that 5 is just an example and K can be arbitrarily large. So these vertices could have like up to K vertices each, and because K is unbounded, we don't get a bound that's independent of K on our separator size. So we need to work a little bit harder than this, but this is a start. And the way we proceed from here is we say, okay, so we can't take all of these super vertices, but we can take some of them. So in particular, we're going to take all of these ones that have size at most 4. So we would take this one, we would take this one, and this guy we're going to have to deal with in some other way. And 4 might seem a little bit arbitrary. There is a reason for it, but what matters is we're taking all the ones that are below a constant. So we know that this set will also have bounded size because we're just taking 4 times something that also has bounded size. And so the question now is, how do we deal with these guys that can have size up to K? And so here's just a bit of a summary of that. And so we're going to denote the bad super vertices, as in the ones that are too big, by B, and their set of representatives is going to be denoted by Y. And so now we're going to do something kind of similar that we did with H prime, but we're going to do it again. So we're going to define this new induced minor called H double prime. And the idea is as follows. So if we took, as we said, if we took all of the vertices that we get from H prime and removed all of those from H, we'd get a balance separator. So we're going to let D be the components of H if we had removed all of those vertices. So in particular, each of these components has weight at most a half. And now, because we couldn't actually have removed the bad super vertices, we're going to add those back to the graph. And so that's kind of what n is here. So this y here is the representatives. And then we have n here, which is all the neighbors of the representatives are the vertices corresponding to B. And so now we're going to get this bipartite graph here. If we ignore y, we have this bipartite graph between n and d, where these edges just correspond to adjacencies in H. So each of these guys is a vertex of H. Each of these guys is a component of H. So if this guy has a neighbor in this component, then there's an edge here. And now we want to bound the tree width of this graph, and we'll see why in a second. And to do that, we're going to use this theorem of Korhonen, which says that if a graph doesn't have a big wall as an induced minor and it has bounded maximum degree, then it has bounded tree width. And recall that one of the points of the theorem is that H doesn't have a big wall as an induced minor. And because H double prime is an induced minor of H, it also cannot have a large wall as an induced minor. So we kind of get that part for free. And what remains is to bound the tree width of H double prime. And so I guess a keen audience member might have noticed that we haven't used anything relating to outer string graphs yet. And this argument shouldn't work if we don't use it because G has unbounded tree width. So we're going to have to use that in this step. And the way we do that is we use it to bound the degree of these components. So we can start with these little guys from N. These are easy. Just from the structure of G, they have to have degree at most 3. So that's easy. And the question is, how do we bound the degree of these guys in H double prime? And the key is to notice that Y has bounded size because it's the representatives of super vertices from B, and B is a subset of X prime, which is our balance separator for H prime, and H prime has size X prime has size at most 3. And so that means that there can be at most 3 of these guys. And so what happens if the degree of one of these components is too large? Well, by a pigeonhole argument, 3 of its edges will have to go within one of the members of Y's neighbors. So we see here that this vertex of H double prime has degree 5. And because there are, I got a chat. 1 second. Okay, sorry about that. I lost me. There we go. So as you see, if we use just a pigeonhole argument, if the degree of this guy is too large, then 3 of them are going to go connect to one of the vertices of Y. And as you can kind of see from the shape here, this is going to give us a theta. And from the properties of the graph, we can deduce that this has to be a long theta. And this means that this graph is not an outer string graph now because this is a component, but we do some extra work and we can show that there actually has to be a long theta here in H, which of course is not allowed. So we get that this graph now has bounded tree width by the theorem of Korhonen. And because of that, we can get a balance separator for the weight function W prime, which is just the weight function on the components and the vertices according to W. And now it looks like we get a similar problem as before, because again, we can get some vertices from here in our separator, which is fine because these are just vertices of H. But we also have an entire component of H here. So it seems like we haven't really done anything to solve the problem. But notice that if instead of removing this component, we removed these guys here, so the neighbors of the component in H double prime, then this would split the graph like similarly, it would also cause every component to have weight at most a half because these guys we know each have weight at most a half. And conveniently, we just showed that the degree of these guys is bounded. So if we switch from including this in our separator to including these guys in our separator, we gain at most a constant factor. So we multiply the size of our separator by a bit, but now we know that the balanced separator consists entirely of individual vertices of H and not entire components of H. So to recall, we found a balanced separator for H prime, and we used it to get a separator for H. And then using that, we kind of split our separator into good vertices instead of in terms of being a bounded set and a bad part. And then using H prime, we showed that if we can't replace the bad part by a small part, it has to be because there's a long theta in H, but that would imply that H is not an outer string graph. And so in particular, if there's no long theta, we can run this whole process as normal and we get a balanced separator of H with bounded size independent of K. And recall by the theorem on the balanced separators that if we can find balanced separators for any weight function, then this implies that the tree width of H is small. So that's the end of my talk. This is the paper where we run through these arguments in a lot more detail. And yeah, thank you very much for listening.
Thank you.